Thanks for the introduction. I'm Zeyu Zhang from WhtasApp Infrastructure. I joined WhtasApp about 4.5 years ago and mainly work on cluster scalability, transport protocol, performance tuning, and so on. So today, I will cover the lifecycle of a remote process call in our cluster. And it includes how we overcome the limitation and scale our cluster to more than 40,000 Erlang nodes using pure Erlang distribution, and the service discovery and routing mechanism, the request dispatching and queuing model, as well as the bottlenecks and overload protections we have. After that, I will also briefly talk about the load balancing mechanism that we use. So first, scaled cluster. At peak hour of a typical day, we will have 1 billion online devices, including mobile, desktop, or Chrome clients, meaning 1 billion open network sockets at the same time. Every second, we receive 80 million client requests, including all one-on-one messages, group messages, status change, and so on. On the server side, this results in 900 million RPC requests per second at our server side to handle. So how did we do that? Of course, enough machines. Our Erlang cluster size grew to more than 40,000 nodes now and was peaked at 47K to serve New Year's Eve's traffic. This is a graph of most connected nodes we have. At early 2020, this part, you can see a large growth. It is not us expanding cluster dramatically at that moment, but rather we did a change that merges our small clusters into a super big cluster. So people attend CodeBeam years ago who have seen Anton's talk may know that when WhtasApp got acquired by Meta, we moved from using super powerful machines to relatively smaller machines, which largely increased our cluster size. At that moment, Erlang distribution is not very scalable. We are forced to cut our clusters into small groups. The largest one we have is about 1,200 nodes. We write our own communication protocol between nodes in different clusters, which is called WhenDist. WhenDist is basically a simplified Erlang distribution protocol, but since it's purely written in Erlang, the performance of it is really, really bad. A quite large amount of CPU on each node was wasted on this transport protocol. And it also becomes very hard to maintain after we added a bunch of features to that. So over the year I joined, we dive into the bottlenecks that Erlang distribution has and introduce series of patches. So now, our entire cluster is connected using pure Erlang distribution. They are almost mesh connected. And we all use TLS encryption between any connected pair of nodes. So yes, 40K nodes almost mesh connected. I talked too much about the history. So what have us done? The core part that we do is to disable the global server. Yeah, the first thing that global.erl do is to maintain cluster connections in Erlang distribution. You may have not touched it before, but it's automatically started if you do not specify connect or false. And global is very convenient in small clusters, but not scalable because it does a transactional membership change to all the nodes in the cluster, which is very expensive and slow. Instead, at node boot, we start a Zhang server that caches all the nodes we want to connect to and their IP addresses, and store them in a customized EPMD module. Then we simply sprung a bunch of net kernel connect node processes with exponential backoff. And when node down happens, we just do some reconnect. A special thing we do is to rate limit the connection speed, because SSL handshake is so expensive that if we do all of them at once, the node will just be overloaded and almost all the connection will fail. So if making connections, maintaining the cluster is so simple, like why global is so slow, the reason is that global also provides service discovery. that you can register a process globally and call it from anywhere in the cluster. But in our case, we use the PG module instead, which is much cheaper, and we already upstream it since OTP 23. And locally, we also have a new version of the service discovery mechanism that has more features that we will discuss later, which is called shard PG. Global also provides some other transactional functionality that takes a lock globally, but it's surely not scalable in terms of cluster size as we mentioned. So we never use that, and for each such use case, we have a dedicated macro service to handle this. And during the process, we also found some other bottlenecks and did some optimization in the OTP. One thing I would like to share is that we introduced the kernel TLS offload, which offloads all the encryption and decryption of SSL packets to the kernel space. It's available since OTP 26, and this saves 20% CPU in our entire cluster, like including all the application logic, monitoring, container setup, everything. And so we can have like 20% less machines just because of this to handle the same traffic. You can use it by setting the SSL dist options, but this one only supports certain ciphers and certain platforms. Another interesting thing we want to share is that we did a test in 2020 and found that Erlang nodes cannot connect to more than 32K nodes because each connection is bind to a separate ephemeral port number, and we used up all the port numbers. It's a simple problem to solve, but fortunately, we detect this before we are forced to expand our cluster. And there are some other fixes in SSL applications or kernel application, which made the Erlang distribution now being scalable to everyone now, except you need to disable global. Yeah. OK, so with the cluster connections being set up, we can finally share our RPC workflow. So this is probably the most important slide in the talk, but it's quite straightforward. And RPC definitely needs a server and a client. On the server node, we start the server application and the supervision during node boot. And as mentioned above, PG is the service discovery mechanism that we use in the entire cluster. So we call PG join to publish something like, I'm serving shard 16 of service X. Then on the client side, when the caller wants to make a request, first it needs to know which service and which shard to call. Typically, it's very obvious, like to a specific request, which service you want to call. But shard we pick is usually the p hash of the key. And even for stateless services, we still assign a key for it, which is a quick timestamp to balance the traffic to different shards. And now, given the service name and the shard number, the question is that which process can handle this call? The client will just do a PG lookup, which is just a local ETS lookup that returns a list of remote PIDs, which claims serving this service and shard. We will explain this part shortly, but let's move to the next step. So given the list of server PIDs, we still need to find out the exact PID that we want to send the request to. We have a load balancing algorithm, but because it's very complicated, I will only briefly mention it. Now, we finally able to send out the request. We don't do a Jing server call here because and we do a like simple Erlang send. This is because Jing server call does some extra monitoring, which sends 2 extra Erlang distribution message. We lose the early termination of a call if a remote process died by directly sending Erlang message. But this like direct remote process died very rarely, and disabling it will save the CPU cost significantly. So the request then becomes an Erlang distribution message that goes to the request dispatcher that the server on the server node. So on the server node, we have different request dispatching mechanisms, but the most used one is what we call the queuer. In this case, it maintains a worker pool. When request comes, it finds out if there is a worker available. Once a worker, if yes, it will just send the request to the available worker. And if not, it will just put the request into an internal queue and wait a worker to be available. And once a worker has done its job, it will notify the dispatcher that I'm free, so that dispatcher can later dispatch new requests to the worker. So after the worker has processed the job, it will directly send the result to the caller through Erlang Distribution. And in total, there are just 3 messages happen in an RPC request, like one from caller to dispatcher, one from dispatcher to worker, and one from worker to caller. So that's it for the overview. And now I will discuss the steps in more details. So the first important part of the framework is the service discovery mechanism. Namely, how do a PID publish that it serves a shard of a service, and how do clients find out which process serves the shard of the service? As mentioned above, we use PG module. People who use the PG may already know that, but I have an example here. So, for example, if node A says that PID1 serves group X by using a PG join, and then node B says that PID2 serves group X by, again, using PG join, and when a dist connect node C goes up, it does the PG get members call. It will look up the local cache and get list of the PID1 and PID2. I will briefly explain how it works. Basically, like when booting, the Zhang server will sync its local at cache with all peers by broadcasting a message to registered process on every node. And when a process join happens, it will broadcast the join to all peers. And all peers will receive the update and change their local cache. And when a local join process goes down, the Zhang server will receive a monitor message and also broadcast the update to all peers. And finally, when a peer goes down, the Zhang server will simply clear up all the local cache, the group and PID peers from that peer. So all the algorithm is just this. The propagation of an update in PG is like super fast and cheap, which makes it more reliable than and it is more reliable than a registered process send. For registered process send, it may happen that when the request arrives the node, the request handler may already died or restart with a different state. So you may execute something that you don't want to do. And, but if you do PG leave a few seconds earlier than handler shut down, you likely won't lose any message or any wrong messages being executed. So, and also, there is absolutely no CPU cost if Erlang distributions are stable, which is very important to us. However, even though PG is very efficient, there is still a certain limit on the scalability. In our current cluster, we have 100K service and shard peers, 620K request handlers or dispatchers. This is a quite large number, but not enough. Our boot time for disconnections plus PG propagation already takes more than 1 minute for our most connected service, and this is after a bunch of training. And we don't want it to be much longer. We have databases that has millions of shards, and we cannot afford this many PG groups. So what was done? Previously, we have a 2-layer sharding for the database. Basically, we have a concept of database shard and a concept of service discovery shard. One service discovery shard maps to multiple database shards. And server starts a lot of database shards, but only join a few service discovery shards. And from the client side, it hashes the key to get the database shard ID, and then find the actual service discovery shard in this map. And finally, it can find the actual dispatcher through the PG get members call. So this map is both stored in client side and server side. And obviously, it's obviously they need to match with each other. And everyone who deploys code both on the server side and client side knows that it's hard. And moving a shard around is taking multiple steps of deployment on both client side and server side, which is a big pain to us because we have so many machines. Recently, we have introduced a new module called Shard PG, which solves this problem. I have submitted a pull request on this, but due to API compatibility issue, it's still in discussion state, but it's available to use. With the Shard PG, when node A publishes its service, it just say like PID1 is serving range of shard 1 to shard 16 of service X, of group X. And then node B says that PID2 serves shard 8 to shard 24 of a group X. And when node C wants to visit the shard 13, it can look up the ETS cache and immediately get PID1 and PID2 both serving shard 13. So this is because we use a local cache, which is an ordered set ETS. And there is some algorithm that makes sure it stores disjoint ranges. So searching for a shard is just an adds priv lookup, which is also a feature we added to OTP 27. And now, with all of these, we can move shards arbitrarily on the server side, and no need to think about client at all, because all the required information is propagated through shard PG. So very, very simple for our service owners. Great, that's all I would like to share for our service discovery mechanism, and let's go to the request dispatching, which is this part of the diagram. And currently, to do RPC request in parallel, we run a dispatcher worker model, like everyone does. Our service owners only need to write sequential code, like first read service X, and then read service Y, and then do some computation, and then finally reply to the caller or write to service Z, which is very, very simple. From every dispatcher, we start a static count of worker depending on the service, and then dispatch the RPC request to workers for parallel processing. There are many types of dispatcher we have, but majorly we have three: hash and queuer and sticky queuer. The hash one is the easiest to understand. Basically, given a key, we find the worker that has the hash that the worker number is the hash of the key. And just dispatch the request to the worker. The benefit of it is like fast, cheap, and also simple to understand. But there is a clear drawback. For example, a hotkey may congest a worker and make all other keys that allocates to this worker to fail. And one bad user can impact many random users and cause their request to all fail. So we only use this approach when the request can be done very fast. Namely, it only has local computation and no need to call other remote service or even other Zhang server on the node. The second type, which is majorly used one, is called queuer. In this case, each worker handles at most one request at a time. I have already explained it in the previous slide, but basically, dispatcher will check if there's worker available. If yes, send to a free worker. If no, push to an internal queue. The benefit is that we have more parallelism to handle hotkeys. But the drawback is that it is more expensive than hash method because the worker needs to tell the dispatcher that he is free. For this, we have an in-progress trick that does log-free, message-free feedback. This algorithm is in this link, but I didn't make a concrete model, so I won't have a demo here. And It's only hard to understand code there. But if anyone interested, we can talk offline. It's using atomics. And another drawback is that a single user can use up all the workers by sending many large requests, which is something we don't want to see. This is kind of solved in the next dispatcher type. So the third dispatcher type is called sticky queuer, which we use for read, modify, write operations. This is because with best effort, we want all the operations that related to one key being serialized in one single process. We don't want two workers racing with each other and write inconsistent values. So this is achieved by using something similar to the queuer, but stores a worker ID to key map in dispatcher process dictionary. The dispatcher will keep sending key to the worker if there is already one handling that. And of course, expire a key, a map if the worker is no longer doing that. The benefit is first to make read, modify, write serialized as mentioned. And it also solves the hotkey issue so that one user won't be affect others. So all its requests will go to the same worker. OK. The drawback is definitely more expensive and more CPU cost, because you need to modify the process dictionary. And the flow control we did is basically a size limit of the dispatcher internal queue, as everyone did. We send the timeout together with the request. And if a request gets expired while waiting in the queue, we will also drop it. And we also flush and drop the message if the dispatcher message block is too large by frequently check the process info message queue lane. This is because we don't have anything that prevents message being sent to the dispatcher, and dispatcher may overload or even eventually cause OOM out of memory. Erlang distribution or socket buffer may slow down the traffic when overloaded, but it does not completely stop the traffic, so we need extra prevention. With everything I talk about, the system is still doesn't sound too complex, right? Yeah, so we definitely meet a bunch of issues with that. A very typical issue we see is something like this graph. It describes a test that we do that we increase the traffic over time, and the traffic volume gets higher and higher, which is the blue line. It initially overlaps with the yellow line, which is our good throughput, meaning client actually get the reply. But at some point, the CPU usage spikes to 100%. And starting from that, the good throughput drops quickly to almost 0. I think this happens to also everyone's service. And I would like to share a few simple things that we discovered and would suggest people to check if yours has the same issue. So first issue is a well-known issue that Erlang object collection does a linear scan to the process heap every time. And the GC time linearly grows when process heap grows. For us, both the internal and the external message queue of the dispatcher uses memory. And when there are lots of requests pending, the heaps becomes larger and larger. And eventually goes to a state that it cannot do even receive loop faster than the speed of incoming request, and leads to a death spiral. To solve this, it's quite simple to set the external message queue to off heap. This is a feature introduced in OTP 19, and any process that could get a limited message queue is suggested to use this flag. For the internal queue, we just implement an ETS-based solution that moves the queue out of the heap, which is not cheap, but it solves our problem. The second issue we met is that under high CPU utilization, there can be a long run queue for the Erlang schedulers. Process may have a long latency before they are getting scheduled. And because the default Jing server call timeout is 5 seconds, it may happen that some library applications start to crash because of the timeout, because the Jing server is not scheduled for 5 seconds. And this causes cascading failures. So the solution we did is to have a high priority process monitoring Erlang scheduler utilization very actively, and update the value in an atomic array. If scheduler util is larger than 90%, with some probability, we will not dispatch the job to the worker and put the request in the internal queue. So the CPU utilization will keep around 90%, and the library application will be able to do things. This might look like wasting of CPU, but it's actually not. Because at larger than 90% CPU, it is really hard to tune the service. And the last 10% is very easy to not follow a linear growth with the traffic, as what I've shown in the previous graph. So the third issue is that we mentioned we have an expiring logic for the request in the internal queue. But we actually found that processing nearly timeout requests also doesn't make any sense. Because even you have processed the job at the time that your reply arrives to the client is very likely already gave up. So it is wasting server resources and introduce endless retry loop and making things even worse. The solution we do is to first fully propagate the timeout on each RPC request. Namely, if I request the several external calls sequentially, the second one shouldn't have timeout longer than the total time which was left. So if the total call is 10 seconds, the first call takes 7 seconds. The second call, no matter how much timeout you set, it will only be 3 seconds. And also, if an internal queue is not empty for a certain amount of time, we will drop the request if not more than half of the time left. This is pretty aggressive, but this is what we currently do. The fourth issue we see is related to spawning processes. We have a great parallelism framework as we described, but some people still want to do things more parallel. Yeah, which then causes an issue. We found that every process spawn takes a process table log, and this limits how many processes can be spawned per second because it's a single-threaded log. Some of our service spawn 1 or even 10 processes per request, which causes the issue. The general guideline is definitely spawn as least number of processes as possible and only use pre-existing ones. However, like when we must make a lot of service calls in parallel, the right way is surely do a pre-call computation for each request, then send out the request messages, then wait each replies and do a post-call, and finally collect the results. This is a very straightforward standard approach. But our service owners don't like to write async code. So yeah, internally, we do this with a hacky trick using process dictionary, which allows service owners to write sequential code without needing to split anything into pre-calls and post-call, but still do multi-service call in parallel way in a single process. I don't suggest this as a general solution, so we'll skip the details. But if anyone wants to know, you can reach out to me offline. Yeah, it's a crazy trick. Yeah. Anyway, with the previous and more trainings we have, the final graph looks like this. When incoming traffic increases, at some point, the good put drops a bit, but still is relatively high. The CPU usage becomes closer and closer to 100, but not easy to arrive 100, which is really good for us. OK, finally, the last section, load balancing. I will have, namely, the red part of the diagram. And as I mentioned, the actual load balancing logic we use is very complicated. But the core part is relatively simple, so I will cover it briefly and only have one slide for it. So the load balancing is just to pick the right PID inside of a list of PIDs to route the request to. We usually prefer to route to the data center that is the closest to the client, or even the same client, even the same data center, because it has the least latency. So that's our first filter. Then each PID has a local cached weight that is related to the host capacity, which is basically the number of CPU cores. We have different type of machines even inside one service. So we have to do that to fully utilize all the machines. With given the weight, we use an algorithm called row-reverse hashing. It's an algorithm that minimizes the traffic movement when a PID joins or leaves the list. So this also minimizes the read-modify writes racing that we could see when we deploy the service. In addition, each PID can also have a local atomic failure counter. We can avoid route to the PID if the server is overloaded or the failure rate is too high from reading the atomic counter. So yeah, that's all I would like to share today. Yeah, I know it's very dense, but I have too much to share with you. Any questions?
Great presentation. I'm wondering, since there are a lot of moving parts here, how do you keep track of performance regressions in this kind of a setup? Like, what is your methodology? And
yeah, so we don't change this quite often. Like every change we made, we definitely test what the performance gains and loss from that change. But we also have automatically run performance tests for every service. It basically pushes the service to up to 90% CPU and see how many requests per second that one service can handle. And we keep track of it for like a year or things like that. And we see if the service is not, if regression on the service, yeah.
So when you're selecting the dispatcher, there are the three different types of sticky, the non-sticky, and the simple one, I guess.
Yeah.
Do you have some sort of like static analysis to prevent your developers from making the wrong choice, or do you just code review it? Like how do you make sure that they?
It's kind of service owner's choice, but they will ask us which is the best choice. So most of cases is very obvious. Yeah.
Can you talk more about the including the timeout from the client through the server processes and then back? Are you just storing like, so if it's the client has a 3-second, do you just put 3,000 on the message and then decrement it as you go? And how do you account for the latency of the packet in flight?
So we use the timestamp when it sends out. Yeah.
You use a timestamp. So how do you keep your clocks in sync?
Because our timeouts are mostly seconds, and our timestamps are kind of okay yeah. Like we have relatively good timestamps all over the cluster, so we don't force to sync them, basically.
Fair.
Your client just did a send. Do you include a ref in that send, or do the clients only handle one message?
Oh yeah, we have the ref. Yeah, but we still using the ref, not alias yet. Yeah.
Sorry if you already covered this, but one of the questions I have is for some of the usage of phash2 and some other things, how do you handle changing cluster size or changing anything that would, I guess, trigger resharding?
Yeah, so actually we choose a very big shard count in the beginning, and we never reshard. That's why we have that's why we have 1 million shards, and we need to do a 2-layer mapping as what I have described. And yeah, what the things like resharding is happen on changing the shard map for the second layer, yeah.
We actually do have a question from our virtual audience. Does WhtasApp use process priorities?
Process what?
Process priorities.
most of our process is the same normal priority. Only the system monitoring process that I mentioned is using higher priority. Yeah.
Anybody else? You good? Okay. Well, thank you so much.
Thanks, Sarah.